and I will move to the companion fitting. Okay, so we put a lot of effort in to produce these really nice images, but really we want to get some more solid science out of them, and that's questions, like how bright is this object? What's its separation? What's its position angle? Is there a lot of noise near the planet? We want to get some solid number for what that planet is. So we can do this as well in spaceKLIP. We're using WebPSF and PyClip again. And the way we do that is we can kind of try and model what the shape of the planet looks like. And we can also, in CLIP, model how the subtraction affects the image. So this is kind of what you're seeing here. And then what you want to do is you want to fit this model to the data, like you would fit anything else, really. So the choice of your model definitely matters a little bit. So here I'm showing, earlier I showed you could pick a particular spectrum for the companion. This is really to make this model here. So you can see there's slight differences. I've really scaled this image up, but there's slightly differences between using like a planetary spectrum at like 1200 Kelvin or a stellar spectrum for an A2V star. And for us, I think it didn't make a huge difference and didn't really affect the results, but definitely I think it's good to be mindful of this and not generate a model with a completely different spectrum to something that you're expecting to observe. I will note as well that this doesn't really affect the ability to measure the flux of the companion. That doesn't really change, but what it will do is it changes the shape, which can affect that PSF subtraction and can confuse it a little bit. And then secondly, we generate this model using a particular realization of what the telescope looks like. So here you can see this is a telescope optical path difference map from the wavefront sensing observations, and you can see like slight changes in the wavefront on the telescope itself as a function of time, and sometimes they're more significant, sometimes they're not very significant. But you do want to be careful with how you set this up, and you can do this in spaceKLIP. You can tell it, what date to look at. But you want to pick something that's representative of the wavefront at the time of your observation. At the moment, we can really just do a particular OBD map, but maybe in the future, we can incorporate something more complicated, like interpolating between different OBD maps to kind of get something representative of the time of the actual observation. Okay, so these built-in fitting routines, they leverage things like MCMC or nested sampling to produce things like these posteriors on the right. And you can see, so sorry, the axis labels aren't great, but this is, what's the X position, what's the Y position, so like RA and DEC. What this alpha is, what's the contrast ratio relative to the star, and then L is this like length scale of the noise in the images. And then you can see how these chains have evolved as well for the number of steps you've done. If you're interested in digging into that and seeing if your chains have converged at all. Okay, so when we do this, and when I did this for HIP 65426, what we were finding is the mismatches between the models that we have available to us from WebPSF and data are definitely present. There's slight differences, but they're pretty small, and we can do a pretty good job just using these models to fit our data. Okay, so I will add, there's this one note on uncorrelated versus correlated noise. So this is kind of like a user-informed decision. You need to just be mindful of when you're performing companion fitting. Does the noise look correlated in your image? And then if it does, you might need to adjust the fitting kernel, the way we describe the noise in the model fitting process, if it's possible. And I'll dig into this a little bit deeply, but you can imagine this like, speckles are correlated noise. They have some sort of change as a function of separation. They're not random. And then uncorrelated noise is just this, sort of static white noise, random noise. So what we've found is that actually, if we assume the correlated noise for the near cam images, where we do definitely think we see correlated noise, and you can kind of see this in this image here, you're getting black blobs, you're getting, brighter blobs here, and it kind of looks like there's some substructure here. So the noise is somewhat correlated spatially. And when we try and fit with this correlated noise, the fitting procedure gets a little confused. it starts to think that maybe there's correlations at the location of the planet because the model we have doesn't quite perfectly match the data. So it thinks that mismatch is correlated noise as opposed to, just a mismatch in the model. But when we use the diagonal kernel, so this is like assuming it's uncorrelated, it does a much better job of matching the PSF and instead just leaves behind these residuals that relate to the model PSF mismatch. Now, ideally, we'd love to use this one on the left, but while our models aren't good enough to perfectly describe this data, we really can't, so we have to rely on the diagonal kernel. The only downside of this is because we're assuming this white noise, what happens is it can really underestimate the noise in our images that is this correlated noise we can like physically see. I showed you those kind of spatially varying blobs. So we want to account for that somehow, and spaceKLIP does have the capability to do that. It's very much a backdoor at the moment, but hopefully we can get it more integrated soon. And the idea here is that you subtract away that real planet. So someone mentioned this earlier. So you subtract that away using your best fit model, and then you inject your best fit model, again, a bunch of different separations, making sure you don't get too close to all that gunk that you introduced. And then from that, you want to basically understand the variance in the fit parameters you're getting. What's the variance in the flux as a function of position angle, and that should try and capture that spatial variation as a function of separation and give you more realistic error bars for what the flux of the planet really is. So we scroll down to the PSF fitting. So again, we've got some file stuff. Do we want to repeat centering? We won't bother. What method are we going to use to generate this model PSF? Here we're using WebPSF extension, which is like an extension of the default WebPSF package. You can use WebPSF 2. The only reason we have WebPSF extension built in is because it can have some workarounds to generate PSFs a bit more quickly than WebPSF can. Here's a date we're providing. Please use the OPD from this particular date to generate that model PSF. Then we have a bunch of setup parameters for the PSF fitting itself. Do you want to use nested sampling? Do you want to use MCMC? How many walkers, the burn-in, the steps, and the number of cores you want to use. And then here we have a bunch of parameters for how those fit parameters is set up. So, what's the maximum drift in X and Y of your model you'll accept? Similarly, what's the maximum range in flux and magnitude you'll accept? Correlation length scales, what's the size of the box you want to actually fit? This can be useful. You might not want to fit the entire image. You just really want to focus on the companion. So let's just do a box around the companion of 30 by 30 pixels. This is where we put in the kernel to fit the noise. So here it's diagonal. And then we have some extra things for the width of the annulus for the noise map and the radius around the companion that's not included in estimating the noise. So if I hit that loads all the parameters in again, and then we can run this pipeline.companion step. I do think this will take a little bit longer, but I'll just show you here. It's generated this new companion folder, and it will chuck files in there as they're available. But here you can see it's KL20. So we're doing it for the mode with 20 PCA modes in our subtraction. Just because this might take a while, this could take sort of 10 to 15 minutes, I think, for this kind of observation. But I will show you one that I ran earlier for the same thing, so we can actually see how long it took here from the file creation. Oh, okay, no, it's not too clear, but you can see what it's generated here. So in fits, we have some files for, and I realized yesterday a bug. Hold on with me. Somehow DS9, if you put a file name too long in DS9, it just crashes when you open it. So we're working with that issue right now. But if I do this here, we can see this is the model of the PSF. Put it on this. You can see this is the model, and then this is the data we're fitting to, and that's what it's going to do. It's going to use this to fit that, basically. And then here is some sort of results. So all the chains are saved in a pickle file. You can also view that PDF. You can view the corner plot I showed you. You can look at the PSF that was fit at the end. So that's that kind of image there. You can look at the forward model PSF. So this is just those two images I showed earlier in DS9, just in a matplotlib instead, pointing out where the companion is. It can show you, this is what the data looked like. This was your best fit model, and these are the residuals that were left over at the end. And there's this transmission plot as well, just showing you, what the transmission is spatially. So that's basically that process there. So you can imagine you can do this for whatever KL mode you want. It will generate new filters. And you can also imagine, you can repeat this process for a whole bunch of different filters and KL modes, sorry. So yeah, you could do different KL modes here and they'd saved in this folder. You can have a different folder for the filters, different subtraction modes, ADI plus RDI. You can compare to RDI, you compare to ADI, see what's working best for your particular observations.